Welcome back, everybody. In this video, we're going to talk about one more proof technique that, to be completely honest, we won't use all that often. But it is important, and when we do need it, we'll need it. So we're going to go ahead and include it here. And it's a proof technique, so you think, why didn't we do this, ages back when we were first learning how to do direct proofs and proofs by contradiction and so on? The answer is, well, we really didn't need it till now. And the second thing is, it fits better here since we just talked about cardinality. And the star of the cardinality show was the natural numbers, right? Because we imagine the natural numbers, each one being on a post-it note that we could go around and stick on to different things. So the star here is still the natural numbers. So if we were doing algebra, which thank goodness we're not, right, then I would say something like, you know, the integers are a free abelian group on one generator. And then another way you could say that what the integers are is that they're an ordered integral domain whose set of positive elements is well ordered. So I love definitions like this because when my kids were little, I sent them off to kindergarten and they were doing arithmetic for the first time and mostly adding and subtracting, and I would tell them, well, look, if the teacher is getting frustrated, and you're having trouble or anything, just say, look, this is not supposed to be that hard because the integers are just a free abelian group with one generator. and, and see what your teacher says. The kids' teachers always hated me. So since we're not doing algebra, thank goodness, we're doing analysis. I can skip all of explaining what those words mean and just cut to the chase, which for our purposes is this. The natural numbers are well ordered, which means if you have a non-empty subset of the natural numbers, then it has a minimal element. Now, think about what that says for a second. It's sort of like, well, duh. You give me a whole bunch of natural numbers. Remember, natural numbers start at 1. That's the point. They go 1, 2, 3, 4, 5, 6, and so on. So if you give me a bunch of natural numbers all in a bag, then there'll be a smallest one, right? If you could take a subset that was infinitely big, there might not be a largest one, right? For example, if you start counting, from 3, 4, 5, 6, and keep going, then there won't be a keep going forever. There won't be a largest number, but there'll definitely be a smallest number. It'd be the 3 where we started. So every non-empty subset of n has a minimal element. That's a really useful thing because it leads directly to the principle of mathematical induction, which is our goal here. So this gives us a cool way of proving statements about that are true for all the natural numbers. So for example, suppose that we have a statement like p of n, and that's a statement for each of the natural numbers, and we want to prove this is true. So what kind of statement might this be? Well, the kind of thing we might care about in this class, where we're really trying to think about the theory behind calculus. I'd kind of like to prove something like, um, the power rule. If I take the derivative of x to the n, that should be, we bring down the n and make it x, or n times, say that again, n times x to the n minus 1, right? And if you try to prove this, with a particular number, like it's not hard to take x squared, plug it into the definition of the derivative, and do some algebra and some calculus, and out comes 2x. You try this with x cubed, and you do the work, and out comes 3x squared, and so forth. But I don't want to do all that. I want to prove that it always works for every n. So that's a statement like the kind we're talking about here. A p sub n is a statement for each n. Now, one way to prove this, right, would be to use a direct proof or a proof by contradiction or whatever, but the really slick way to prove this is using induction. And the way this works is we first assume that p of 1 is true. Okay? So first we have to check that it works for the very first number. And we try that. P of 1 is true. Next, we just have to prove that if, this is an implication we're trying to prove, if this works for p of k. In other words, if p of k is true, that implies that p of k plus 1 is true. Okay? So you can imagine it like this. The first condition, A, says that I can knock over the first domino. So imagine that I have a domino for each natural number stretching off into infinity, and each domino is the statement, P sub k for some k is true. So if the first domino is true, right, the first statement is true, I can knock over that domino. The second thing I have to prove, what number B is saying, is that whenever pk is true, then the next domino, pk plus 1, is true. So when I knock over, domino k, that will automatically knock over the next domino in line. Okay? And if you could prove those two things, that you can knock the first domino over and that every domino knocks over the next one, then all the dominoes get knocked down. And so Pn must be true for every n. This is really cool because I don't have to then try to prove it for every possible n. I really just have to check two things: that I can knock over the first domino and that every domino knocks over the one after it. Here's an example of the kind of thing that shows up, and we'll need this formula again, later. So if you start adding up all of the um, numbers 1, 2, 3, 4, 5 up to n, then there's a shorter way to do that than adding up all those numbers by hand. It's just 1/2 times n plus 1. Now, there is a direct proof for this, which I like a lot. And in fact, I'm going to tell you what it is because I'm going to tell you a story. So, one of the most famous mathematicians, some people say he was the last mathematician that understood all of mathematics because mathematics is so big now. There's so many different fields and subfields and sub-subfields of mathematics that no one ever understands anything beyond, professional mathematicians don't understand anything beyond what the part that is that they work on. So, but everybody says that Carl Friedrich Gauss is probably the last mathematician who understood all of math that existed at his time. And when he was a boy, he was apparently somewhat troublesome, and, and smart kids often are. And this teacher decided to punish him and told him to add up all the numbers from 1 to 100 because she thought that'll take him forever. And apparently, he used this formula, even though he was only like 6, and got the answer and figured out the formula on his own. And so, one easy way to figure out that this formula has to work is this. Suppose I want to add up all the numbers from 1 to 100. Then, what I could do is, using the ideas that we talked about pairing up things with cardinality in previous videos, I'll grab 1 and I'll grab 100. Stick those together. That makes 101. Then let's grab 99 and 2. Oh, look at that. That makes 101. Then grab 3 and 98. Oh, those make 101. Right? So you see where the n plus 1 is really coming from. If I go through and pairing up the biggest number and the smallest number, I'm making pairs every time, they all add up to n plus 1. And how many of those pairs are there? Well, I'm making pairs, so it should be half of n. So that's, one way of seeing why that formula should be true. To prove this with induction, though, is also enlightening because it gives us some insight into the way induction works, and it's not very hard. So we'll let P of n be this statement that when you add up the first n integers, you get 1/2 n times n plus 1. So what do we have to do? First, we check what happens with the first domino, right? So when I plug 1 into this formula, I would get 1. That's as far as my sum goes, right? On the left hand side. And on the right hand side, I'd get 1/2 times 1 times 1 plus 1. And lo and behold, that turns out to be 1. So the first domino gets knocked over. P of 1 is obviously true. So there we go. Step A in the proof by induction list is done. Next, we have to show that every domino knocks over the next one. Okay, so how does that work? We assume that pk is true and have to prove that implies pk plus 1 is true. So we're going to assume that when I add up 1, 2, 3, 4, 5, 6 up to k, that actually does equal 1/2 times k plus 1. All right, and so what I want to, that's what I'm assuming, right? I'm going to do a direct proof of this implication. I'm going to assume that pk is true and then prove that pk plus 1 is true. So this is the maybe the most important part here. Let's carefully write down what p of k plus 1 actually says. Because when we talked about direct proofs, I said, if you're trying to prove that p implies q, the typical thing is you start with p and say, okay, I've got p, that's what I know. What does that tell me? Then go look at q and say, okay, that's what I want to prove. do I know anything that tells me that, and then try to connect the dots. So what is it that I'm trying to prove here? What does P of k plus 1 say? Well, that would say that if I add up 1, 2, 3, 4, 5, 6, 7 up to k, and then add on k plus 1, that I get on the right hand side, well, now instead of k and k plus 1, I'll have k plus 1 and k plus 2. Because remember, what I'm doing is substituting k plus 1 into this formula. So 1 half k plus 1 times k plus 2 is what this should add up to be. Well, since we assumed that p of k was true, then when I add up the first k numbers, colored in brown there, right, then I know what the formula is for those. Right? So the first k numbers in brown add up to a brown 1 half k times k plus 1. And now I've just tacked on an extra green k plus 1, the next number after k. Okay, cool. So now all I have to do is take the last line on the screen there and turn that into 1 half times k plus 1 times k plus 2. So this is that similar pattern that we've seen over and over again about how to prove, something, an implication with a direct proof. We've figured out what our P, if we're doing P implies Q, we figured out what P says, we figured out what Q says, and so now we just have to connect the dots. Okay, well, if I look at that, there's a bunch of K's there, right? There's a 1 half, which is a good thing, but the 1 half is only being multiplied by the K times K plus 1. The 1 half isn't being multiplied by the rest of it. So let's do this. Let's go ahead and factor out a 1 half from the whole thing. So what I mean by that is factoring out 1 half out of the K times K plus 1, the first term, is easy. Factoring a 1 half out of that green k plus 1 is not quite so obvious what I mean by factoring out a half, because there's not a half there. What I really mean is put a 2 there, and then I could factor out the 1 half. Everybody see how that works? If you're not sure how I got from the top line to the bottom line, then go backwards. Right? Obviously, if I distributed the 1 half through there, I get back to what I started with, because the 1 half would cancel with that purple 2. Okay? Now, the cool thing about this is, you see I've got a 2 that showed up in my equation now that I didn't have before. And what I should end up with when I'm done is 1 half k plus 1 times k plus 2. And if you start with the last line there, look, I could factor out a k plus 1, a black k plus 1 from the first term, the green k plus 1 from the second term. So if I factor out the k plus 1 term, that just leaves me with k plus my purple 2, and that's exactly what I wanted. So that was really easy. All I have to do is assume my P of k was true, do a whole bunch of algebra. I proved that P of k plus 1 was true. In other words, that each domino knocks down the next. So this P of n, right, this statement formula that I wanted to prove, has to be true for all n. Here's another example. This is one of my favorites. I love showing this to kids who've just learned how to do multiplication, or sometimes teachers in elementary school, because this is so cool. This works out this way. If you add up the first n odd numbers, you get n squared. Okay, so think about that, right? So if you add up 1, well, let's just try 1 plus 3 gives you 4, right? 1 plus 3 plus 5 gives you 9. Wow, that works. Isn't that cool? Right? There's ways of proving this by using triangular numbers and dots and some cool things. But let's do this with induction. Right? So I'm going to let P of n equal this formula, that 1 plus 3 plus 5, whatever, all the way up to 2n minus 1, that equals n squared. Okay. Well, check P of 1. Yeah, that works, because the first odd number is 1. That's all it is, so I don't have to add up anymore. And 1 equals 1 squared, so we're good. Check that one off. Now we have to do the induction step. We have to show that every domino knocks down the next. That P of k being true implies that P of k plus 1 is true. So we assume that the formula is true when I plug in k. Then when I add up the first k odd numbers, I get k squared. And carefully writing out what it would mean for P of k plus 1 to be true, right, you see that what I get is the brown part. That's the sum of the first k odd numbers. Then I tack on the next odd number, and that should turn out to be k plus 1 squared instead of just k squared. But this is really, really easy now because since we assumed that pk was true, I'm assuming that all those brown numbers there in the sum add up to k squared. So I just replace all those first k odd numbers being added there with k squared. And now look, k squared plus 2k plus 1, oh wow, that factors, right? That factors into k plus 1 squared, which is exactly what we were trying to show. So sure enough, when you add up the first n odd numbers, you get n squared. Now, one thing I should probably mention, because sometimes this proves useful also. What we've described induction so far is showing that you can knock over the first domino and that every domino knocks over the next one. That's exactly what we have on the screen here. But there is, well, not really a better way, but sometimes a bigger gun that we can use to prove a theorem. And it's this: instead of part B, which is assuming that or proving that every domino knocks over its neighbor, we could do this instead. We could prove that every domino and all the ones before it being knocked down knocks over the neighbor. Why does this make any difference? Well, if you need to prove some things that are really tricky, assuming pk might not be enough. This lets you say, okay, I can assume that p of 1 is true and p of 2 is true and p of 3 is true all the way up to p of k. In other words, all the dominoes behind me have already fallen down. Okay? That gives me k different equations that I can use if I'm trying to prove some kind of equation. And very often, putting together some of those earlier equations with p of k will be enough to prove that p of k plus 1 has to be true.